Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Series. And I'm super happy to have AAS Journal author Akira Harada with us today. Hi, Akira.
Hello, Frank.
Where are
How
you?
about you?
Where are you located at? We have a little bandwidth lag. We need to be patient. So I'm doing well.
Yeah, thanks.
You go.
I'm fine. I'm doing well. I'm in now about the north edge of Tokyo. I'm a postdoc in RIKEN Institute.
Very nice. Let's see. We're in, it's April 11th, or in my world, it's April 11th. In Phoenix, it's April 12th in Akira's world. We go across, but it is April nonetheless. Is spring happening in Japan? Are we getting little blossoms on the trees?
Yes, very beautiful full bloom of blossom. Yeah, RIKEN has a lot of cherry blossom trees, full bloom of cherry blossom about several weeks ago.
Oh, nice. Very cool.
But now recently in Japan, almost summer.
Wow.
Almost, yeah, it's about 25 centigrade.
Okay. Okay. It's
very hot.
Might be a little hotter in Japan this year.
Yes.
Yeah. And speaking of beautiful, that's a beautiful background image that you have there. What is that?
Yeah, thank you. This is my first supernova simulation. The supernova is my major.
Very nice. Very nice. Very pretty. Cool. And speaking of, Akira, what do you like to do for research?
Yeah, I'm interested in the explosion mechanism of core collapse supernova. I want to understand it by using numerical simulations.
Very nice. And that is going to bring us to this very lovely APJ article, open access, everyone, go get it. Prospects of fast flavor neutrino conversion and rotating core collapse supernovae. And Akira, take us away.
Okay, thanks. Yeah, this is my recent paper about the fast flavor conversion in the core collapse supernova. Yeah, first of all, let me summarize the supernova. Yeah, the core collapse supernova is the explosive death of massive star. Yeah, you may know that the massive star makes iron core at the center. At the end of the evolution, the iron core collapses and bounces due to the nuclear force. Then the bounce shock is launched and it eventually stalls. And then the center, after bounce, the proto-neutron star is formed at the center and it emits energetic neutrinos, hits up the shock, and then the shock revives. This is or promising scenario of the quark supernova explosion. And the neutrinos plays very important role. Actually, as I said, I'm investigating this by numerical simulation, especially for the Boltzmann neutron transport simulation.
Okay.
You know the neutrino, yeah. Neutrino is the only weakly interacting particle, and it is not in equilibrium, thermal equilibrium. We need to trace neutrinos in 6-dimensional phase space.
Right.
Of course, it is very computational heavy, but we managed to develop the Boltzmann equation solver for neutrinos and apply it to the supernova simulations.
I'm with you.
Yeah. And yeah, neutrinos is very important. And recently, collective neutrino oscillations is gathering attention of the supernova fields.
Yes.
Yeah, you know the neutrino. Yeah, you know the neutrino oscillation is a phenomenon when the phenomena that the neutrino changes its flavor along its flight path. And if there is electrons on the path, the interaction between neutrinos and electrons changes the behavior of the oscillation. You know, it is called the matter effect or MSW effect.
Yes.
And yeah, but neutrino also interact with neutrinos itself. This becomes important if the neutrino density is high enough in the environment such as supernovae.
Okay.
Then neutron interaction may change the behavior of the neutrino situation. This is called the collective neutrino situation.
Yes.
So especially fast flavor conversion or fast pairwise flavor conversion is gathering the attention. Yes. And this phenomena is, due to the neutron-neutron interaction, the electron type neutrinos changes to mu type or tau type neutrinos. At the same time, mu or tau type neutrinos is converted to the electron type neutrinos. So it is a kind of swap. That is why it is called pairwise.
Okay.
Due to this, if it occurs, spectrum of electron neutrinos and heavy lepton type neutrinos can be mixed. And it should, because of change of the spectrum, it should affect the heat neutrino absorption or neutrino heating of the supernova matter, and it should affect the explosion mechanism of the supernova. But because if this collective neutrino situation is complicated, the understanding is now underway. I'm sorry, I forgot to mention about the fast. There is several modes of collective neutrino situations. Fast flavor conversion is one mode of that. One of the modes. Fast means is a conversion time scale or length scale is very, very short. It is about meter scale. Okay. It is enormously shorter than compared to the astronomical scale.
Right. Or yeah. Yeah. Good. Okay.
Yeah, and the fast flavor conversion or collective neutralization is described by so-called the QKE quantum kinetic equation. And it is a nonlinear equation of the distribution functions or density metrics. Because of such short physical scale, the nonlinear feature makes the problem very, very difficult. Okay. So yeah, so currently there is two ways to simplify the problem. One is to consider simplify the background, reduce dimensionality. Yeah. But solving the nonlinear equation. And another way is to consider the linearized version of the equation to check whether the fast flavor conversion can take place or not. Yes. And thanks. And I'm doing the latter way. I'm checking the whether the FFC fast flavor conversion can take place or not. Okay.
Your approximation. Yep. Okay.
Yes.
Good. Great.
Yeah, and I said, very, very recently, a lot of works are dedicated to investigate the collective neutrino situation, and there is a theorem that some author found some necessary and sufficient condition for the fast occurrence of the fast flavor conversion. That is called the electron neutron lepton number crossing, or ELN crossing. I will explain later. So our linearized investigation becomes the search for the so-called ELN crossing. Okay. And this is a relatively simple problem compared to the full QKE, but there is still a difficult point because the ELN needs information of the distribution function itself in the six-dimensional file space. So you can guess how it is difficult. So the work so far almost work so far relies on some approximations. However, we have Boltzmann solver and we can extract the distribution function from the supernova simulation directly, and we can use it to check the electron and crossing.
Right.
So sorry, I forgot to mention about one thing.
Okay.
Actually, Nagakura, my co-author, developed a special technique to a reliable technique to check the ELN crossing calculated by the Boltzmann solver. He found that this FC commonly occurs in the quark supernova. However, he only focused on the supernova without progenitor rotation. In this paper, we found the stellar or stellar rotation, progenitor rotation can induce the collective neutrino oscillation or ELN crossing. So I reported here that.
Cool. Very good. All right. Let's see some of those results. Now we're both got our trim. How about that?
Okay. So let's go. Shall we go to numerical setups?
Sure. Let's do that.
Okay. Yeah, actually, we are running the supernova simulation with progenitor rotation. Yeah, we start with the 15 solar mass progenitor. We evolved without rotation, and I impose rotation as the initial condition of the stellar collapse. Yes, equation 1 is impose profile of the stellar rotation. Yeah, the central 1,000 kilometer rotates rigidly with 4 radian per second, and outside the rotation rate drops with R to the -2. Yeah, and I ran the Boltzmann supernova simulation with these initial conditions. Yeah, the setup is listed here, and yeah, the summary. Yeah, and summary of the simulation is in figure 1.
Let's take a look at figure 1. Bang.
Yeah, the top. Thanks for magnifying.
And we can zoom.
Yeah,
in.
the top. Thanks. Yeah, the top. Actually, the simulation is still going on. Yeah, the top panel is.
I'll come back to that.
Trajectory of the shock radius. The solid is angular average, and the thin lines as max and minimum. Yeah, top panel. Yeah, that's thanks.
Okay.
Yeah, the solid line is for our rotating models, and that dotted line for our non-rotating counterpart.
Okay.
Yeah, seemingly the non-rotating models does not explode. Yeah, the shock radius is shrinking.
Right.
So I stopped the simulation at some point. And for the rotating model, the shock is very gradually growing, very gradually. So I still not confident whether this model explodes or not. Okay. So I'm still going, running. Anyway, on the way of the simulation, I found the collective neutrino session. Anyway, this is the basic information to understand what I am doing. Yeah, yeah. The second middle panel is the neutrino luminosity. Yeah, red is for electron type neutrinos, blue is for anti-neutrinos, and
Okay.
black is new. Yeah, black is new X. New X means heavy lepton type neutrinos. Collectively, mu type, tau type, and they're antiparticles.
Okay.
Yeah, in our setup, these 4 species are identically treated, so they are collectively denoted by new X.
Paradigm in that.
Yeah, and again, solid is rotating, and dash dotted is non-rotating.
Yes.
Yeah, and the bottom panel is mean energy of neutrinos.
Ooh, okay.
The legend is similar. Yeah, these are the basic quantities of my supernova simulation, but
Wow.
yeah, this is just describes this is just to describe what is I'm doing for the supernova simulation. And yeah, what is important in our numerical setup is next equation 2 and equation 3. This is electron ELN. Yeah, actually equation 3 is ELN, this G. Yeah, this G. Yeah, equation 3.
Yep.
Yeah, here F is the distribution function. Subscript nu E and nu E bar is you can guess electron type neutrinos and its anti-neutrinos. Yeah, its difference is integrated by its energy. Here GF is a Fermi constant. This quantity 3 is called the electron lepton number. There is a theorem that if sorry, I need to explain more. Yeah, the argument of G is omega nu. This is direction of the neutrino momentum.
Okay.
Okay. Then let me just explain the theorem that the necessary and sufficient condition for the first occurrence of the first flavor conversion is that the electron lepton number has both positive and negative parts with respect to this omega nu. This is called EL crossing. Yeah, if G is positive, there is more neutrinos in that direction. If G is negative, there is more anti-neutrinos in that direction. If G has both positive or negative, depending on the omega nu, there is some point of crossing where the electron type neutrinos and its anti-neutrinos distribution crosses.
Yes. Yes.
Yeah, that is a theorem found by Morinaga et al. Yeah, refer to as just above the equation 2.
Okay.
Also, Morinaga found some approximate formula for the first flavor linear stability analysis of the FFC. That is equation 2. Yes. So, as is the case of the linear analysis, we calculate the linear growth rate of the perturbation. Here, perturbation means mixing of the different flavors of neutrinos.
Okay. Okay.
Yeah.
Yep.
The growth. Yeah, and this growth rate is the linear growth rate of this linear problem. The first factor means the integral of the ELN where over the angular region where the G is positive. And the second factor is the integral for the G negative. So it means if G has ELN crossing, the sigma becomes real positive, and it means growth of the linear perturbation. Then it can be interpreted as occurrence of the first flavor conversion.
Okay.
And yeah,
Yes. Very cool. Yeah.
Yeah. Sorry, my complicated explanation, but in short, we calculated this equation too by using the distribution function we obtained on search for the search where the crossing takes place.
I'm with you.
Yeah,
Good.
and so could you go to figure 2?
Let's go to figure 2. Figure 2, let's throw that up. There we go.
Yeah, this is this is the main result. Yeah.
Okay.
I'm showing the snapshot of the growth rate. Yeah, by color map.
Yeah.
Black region shows the growth rate 0, so there is no EL crossing. And I'm comparing the rotating model and non-rotating model.
Yes.
White line shows the shock position of the shock wave. You can see that in the non-rotating model, there is no region where the growth rate is non-zero, so there is no fast flavor conversion. However, in the left part is rotating counterpart at the same time, about 165 milliseconds after the co-bounce. Yeah, you can clearly see that the islands of large growth rate. Yeah, it reaches maximally 1 meter inverse.
Oh, there we go.
So yeah,
Yep.
the growth rate is very growth rate is large, or growth length scale is very short. Yeah, so seemingly because these islands only appears in rotating model, the rotation plays important role to make this region.
Yes.
So in the rest, we investigate how rotation affects this.
Okay.
Yeah. Sorry.
All good.
I marked the blue cross as almost the largest growth rate point.
Yes.
And the figure 3 shows the ELN distribution as this blue cross.
Okay.
Yeah.
Okay. Okay.
Oh.
Mullenweed.
Sorry, not so good figure resolution. Anyway, yeah, this is a model-wide projection of the ELN at the point. Yeah, you know, the ELN is a function of omega, so it can be projected into model-wide diagram. Yeah, blue shows the ELN positive. It means there is more neutrinos in that direction. And red means there is more anti-neutrinos in that direction. Yeah, you can easily see the. Oh, are you okay?
I'm fine, thank you.
Okay, good. Yeah, you can see that in the radial direction at the top, the end is less, so there is more anti-neutrinos. On other direction, there is more neutrinos. So EN crossing takes place in the white regions around the ER. Yeah, actually.
Okay, cool. Yeah.
Yeah, it is natural. How say? In the supernova, the neutrinos are naturally more abundant than anti-neutrinos. So blue region is natural, but so we need to know why anti-neutrinos is abundant in the radial direction.
Okay.
So then let's go to figure 4.
Figure 4, FFC.
Figure 4.
Ooh, okay. Here we go. Let's take a global shot first, and if we need to zoom in, we'll zoom in. Okay.
Yeah.
Radial profile.
Yeah, this is a radial profile on the equator. Yeah.
Okay.
Sorry, can you see? Sorry, can you go back to the figure 2?
Sure.
Yeah, we horizontally slice this figure at the z equals 0. Then the profile along that slice is shown in figure 4.
Okay, and you're going to pick up this thing. Okay, got it.
Yes.
I'm with you. Okay, and we'll take a full shot so we get the full. If we need to zoom in on one of these, we will, but now we get the total.
Thank you for showing the whole figure. Then the radial profile from 0 kilometer to 200 kilometers. Please zoom in panel A.
Yes, sir. There you go.
Okay, in this panel A, I'm showing the energy integrated distribution function along the radial direction.
Okay.
So if the blue is for neutrinos and red is for antineutrinos, so the difference between this blue and red is just G along the radial direction, or sorry, radially outgoing neutrinos.
Yes.
Yeah, you can see that that's almost everywhere blue is above the red lines.
Almost.
So electron neutrinos is abundant, but in the zoom inset in figure, I'm showing the zoom of some region. Yeah, you can see in this very small region, very slightly, red is above blue. Yeah, very, very slightly. But this produces very large linear growth rate. Surprisingly.
Okay.
Anyway,
doesn't take much. Doesn't take much. Right. A little bit of crossing.
Anyway, this tiny crossing. This is ion crossing found here, and I found this is induced by the neutron absorptions. And can you show equation 4? Equation 4.
Sorry, equation 4. Sorry, my bad. There we go. Equation 4 looks like a radiation entropy.
Yes, this is actually the also so-called the collision term of the Boltzmann equation. Collision term, yeah, the reaction term. Yeah, for the absorption reaction, you know the collision term can be recast into this form: the absorption coefficient or inverse of the absorption mean free path times the difference between the actual distribution function and the Fermi-Dirac distribution function. Yeah, these two factors are important to understand the collision term absorption. So putting this in mind, sorry, can you go back to figure 4 on panel B?
Absolutely. There we go. Oops, a little too big. Right there.
Oh, perfect, thanks. Yeah, this panel B shows the absorption coefficient, radial profile of the absorption coefficient Blue is for neutrinos, and red is for antineutrinos. Here, solid is for rotating model, and dash dotted is for non-rotating model. Here, almost everywhere the absorption coefficient is larger for neutrinos than antineutrinos. You can see
Yes.
the difference between neutrinos and antineutrinos. Sorry, temporarily ignore the vertical lines. Vertical line, I will explain the vertical lines just later.
Okay.
Please. Yeah, please show the absorption coefficient itself. So the difference, please look at the panel B.
Yeah. Can you see that? We just have a little bandwidth lag.
Yeah. You can see the difference between the absorption coefficient between neutrinos and antineutrinos is larger for rotating models than the non-rotating models. Yeah, difference between solid lines is large for solid lines. So it means in the rotating models, this disparity between the neutrino absorption and antineutrino absorption is large. Yeah, neutrino experiences more absorption, but it is significant. Difference is significant in rotating model. That is important to consider the EN crossing. So, sorry, could you go up panel A? Yeah, this is energy integrated distribution function. Distribution function gets decreases with radius. Yeah, this is, of course, this is natural because of the absorption, but yeah, because of the stronger neutrino absorption, the blue decrease of the blue is faster than red. It crosses at this inset. But yeah, in the non-rotating model, yeah, of course, the distribution function decreases with radius, but the difference of the extent of the difference of the neutrino and antineutrino absorption is weaker in the non-rotating model. Read from panel B.
I'm with you.
Results in the no ELN crossing in the non-rotating model.
Right.
Yeah, sorry, it's very complicated.
No, it's good. It's fine. I'm with you. Yep.
Yeah, and the difference of the absorption coefficient is can be read from panel C. Can you go down? Yeah, panel C. Yeah, panel C shows the radial radial profile of the nucleon or neutron and proton distribution, number density of neutron and protons. Yeah, again, solid is for rotating model, and dash dotted is non-rotating model. Now blue is for neutron and red is for proton. Due to the centrifugal force, the matter distribution is more extended in rotating model than non-rotating model. Yeah, dash dotted is drop faster than solid lines. Yeah, but for the non-rotating, for the protons, the drop difference is not so large, but for neutrons, the difference is large.
Pretty significant. Yep.
Yeah, this large difference results in the large difference in the absorption coefficient in panel B, and this results in the large, even stronger electron type neutrino absorption results in the EL crossing shown in panel A.
Yep. Got it.
Yeah, this is why rotation is rotation induced.
Mhm.
Yeah, and
Okay.
I found another interesting thing in panel D.
Okay.
Yeah, this is more a detailed point. Yeah, of course, there is a lot of there is many previous works searching for the EL crossing. Some work suggests that so-called alpha parameter is a good indicator for to search EL crossing even in the approximate Newton transport simulations.
I'm with you.
Here, alpha parameter is defined by the ratio of the anti-neutrino number density to the neutrino number density.
Okay.
Sorry, I might wrote some formula. Anyway, ratio of the anti-neutrino number density to the neutrino number density. Yeah. The previous work suggests that if alpha parameter is close to unity, the EL crossing can take place.
This is the
it is
necessary and sufficient. Got it.
It is reasonable. It is reasonable because it means distribution function of f for neutrinos and anti-neutrinos are close, so it can. So the difference may sometimes be zero, depending on the direction. Anyways, the previous work suggests the criterion is roughly 0.8 or 0.9 or something. However, our rotating model shows 0.7 or something in the presence of the EL crossing. While for the non-rotating model, the alpha is larger than rotating model, but doesn't show the crossing. So yeah, so it is evident that just a ratio of the number density is not always a good indicator. Here, yeah, you can find the reason from the panel E. This panel E, kappa, shows so-called flux factor. Yeah, that is the mean velocity of neutrinos. Yeah, of course, divided by the light velocity. Yeah, and again, the blue is for neutrinos and red is for anti-neutrinos. Solid is for rotating model. Dash dotted is for the non-rotating model. Yeah, in the non-rotating model, the flux factor is not so different between the neutrinos and the anti-neutrinos. So the shape of the distribution is similar between these two species. Yes. However, in the rotating model, the flux factor is more different. So it means the anti-neutrinos is more, sharp or thin shape. Yes. But the neutrinos is more spherical shape. Okay. So the number density itself is smaller for anti-neutrinos, but because of its sharp shape, if we limit the outgoing direction, the anti-neutrinos is abundant in that direction only. Yes. So yeah, so we need to be careful about not only the number density, but also the shape of the distribution.
Right. Yep. Cool. Very good. Take one more global figure 4 here. Just get the global picture here. Okay.
This figure 4 is summarizes our findings of this paper. Finally figure 5 is again shows a global picture of our snapshot. This again shows what the importance of the rotation here. Thanks for showing.
Density. Okay.
The left shows the density distribution, and the right shows the electron fraction YE. The electron number density divided by the baryon number density. Anyway, the thick white line shows the islands where the FFC occurs.
Oh, okay. Oh, yeah.
Okay. And very thin gray line now shows that the density isodensity contour. From outside to inside, 10 to the 8 gram per cubic centimeter, 10 to the 10, 10 to the 12, 10 to the 14.
Okay.
10 to the 14 is hard to see. Anyway, there is the isodensity contour.
Okay.
I'm sorry. And most most clearly 10 to the 10 contour shows that due to the centrifugal force rotation, the matter distribution takes very oblate shape. And due to this oblate matter distribution, the neutrino, so-called neutrino sphere takes the oblate shape. Here, red is for neutrinos and blue is for anti-neutrinos. Inverse. Blue is for neutrinos and red is for anti-neutrinos.
Okay.
I'm sorry. Throughout this paper, I use blue for neutrinos and red for anti-neutrinos. Anyway, you can see that in the polar region, the neutrino sphere for neutrinos and anti-neutrinos are not so different. So the shape of the distribution is not so different between neutrinos and anti-neutrinos. So the crossing does not take place.
Okay. Yes.
However, in the equatorial region, the neutrino sphere for neutrinos and anti-neutrinos more difference is larger. Because of this difference of the neutrino sphere, if we fix the points, the distribution of the neutrinos is more isotropic, but the distribution of the anti-neutrinos is more forwardly peaked.
Yes.
So that is the reason why the FFC or crossing takes place in the equatorial regions.
Cool. Very good.
Finally, in the right panel, this shows why we see islands, 3 islands in this snapshot. This YE map, the yellow shows the electron-rich matter, and these purple arrows shows the matter velocity. You can see that some downflow, downflowing plume,
plumes,
downflowing yellow plume, and outgoing blue plumes. Between islands, there is yellow downflows.
Yes.
Can you see?
Yes, I see.
This downflows is because of the so-called neutron-driven convection, commonly found in supernova. The matter is flowing from shock to center. with heated by neutrinos. So at the shock, the matter is relatively cool, but it is heated going to inside. Then there is so-called negative entropy gradient. So the Schwarzschild criterion is satisfied. Then the convection is derived. This convective motion carries the electron-rich matter to the between the islands. This electron-rich matter prevents the neutron absorption because of the Pauli blocking. Then the reduced reduced neutrino absorption results in the no EL crossing between islands.
Okay, that's interesting. Cool.
Yeah, in short, the convective downflow intersects the unstable fast flavor conversion regions. Yeah, that's all of my findings.
That's quite a lot of findings.
I'll find.
Akira, thank you so much again for walking us through your very lovely APJ article.
Thank you for having me.
Sure. So you mentioned it.
I'm sorry.
You mentioned it a little bit when you were talking, but you know, where do we go over, let's say, the next 2 to 5 years? Do you run other progenitor models? Do you run other rotation rates? Do you run a variety of things? Just sort of where do we go over the next, let's say, 2 to 5 years?
Yeah, next step. Yeah, so what? Yeah, for the short term, we need to check how common for the rotation-induced fast flavor conversion. So yeah, we need to check for other rotation rate models. Yeah, actually, we are running some other rotating models. They are yet to be analyzed, so we will do it. And of course, other progenitor models, other cases are interesting. But what is more important is how this fast flavor conversion affects the explosion dynamics.
Okay.
Yeah, it is.
Except for that, I think you're gonna probably gonna have to do the nonlinear, right? You have to do the nonlinear evolution, right?
Yeah, very difficult. Yeah, I said it's nonlinear and it's the length scale is very short. If we want to resolve it in the running superposition of the required resolution is very large.
Right.
So it is almost prohibited. So we are considering to make some subgrid modeling.
Correct. Yep.
Yeah, that is in some small region where we can approximate the uniform matter background. Then we run the full quantum kinetic equation in that small region, and get asymptotic state. Then we can get the relation between the initial distribution of distribution function to the resultant asymptotic state, where the spectrum of neutrinos and heavy lepton type neutrinos are mixed. Then it can be fed back to the global supernova simulation.
Yeah. Okay. Cool. Very nice. Well, I look forward to seeing those simulations over the next couple of years. That'll be really nice.
Thanks.
All right, and that'll do. Akira, thank you so much again for being with us and talking about your paper.
Yeah. Thank you from me to introduce me here.
Absolutely.
introduce our paper.
Cool. And that will do, everyone. Bye-bye. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one.